Okay, we want to continue on the subtopic of supersonic flow over wedges and cones, right? So basically, we will spend around 40 to 50 minutes to look into the subtopic of 3.3 as well as 3.4. And right after the break in 50-minute times, we will then try to complete these remaining subtopics of 3.5, 3.6, and 3.7. So let us look into the supersonic flow over wedges and cones. From our early understanding of oblique shock wave, so you have to refer back to the last week lecture. We note that the wedge is a two-dimensional 2D profile as in figure below. So this is the figure that we are talking about, the wedge. This is the wedge, right? It is a section of a body that stretches to plus or minus infinity in the direction perpendicular to the pitch. So the wedge flow is by definition two-dimensional flow, and our previous 2D oblique shock theory fits nice in this particular case, right? So let us read through the remaining text over here. In contrast, if you are referring to the previous figure, we know that the flow over a cone of three-dimensional body, right, which is being denoted in this particular figure, right, experiences three-dimensional relieving effect compared to the two-dimensional wedge just now. That is, in comparing the wedge and the cone, so you have the wedge as well as the cone, so both with the same angle of 20 degrees. So this is the angle theta, okay, of 20 degree. The cone also having theta angle of 20 degrees. Okay, so the flow over the cone has an extra dimension because it is 3D, and hence it is more easily adjust to the presence of the conical body in comparison to the two-dimensional wedge. So in short, the main differences between the supersonic flow over a cone and wedge, both with the same body angle, let's say 20 degree, are that the shock wave on the cone is weaker, right? And the cone surface pressure is less. At the same time, the streamlines above the cone surface and curve rather than straight, right? So let us look into much more analysis of on here. As a summary, if you're comparing the two situations just now, the wedge and the cone, the analysis of the supersonic flow over a cone is more sophisticated than the oblique shock theory. Okay, the calculation of the supersonic flow over a cone is discussed in a much advanced topic of aerodynamics. However, it is important for you to recognize that conical flows are inherently different from wedge flows and to recognize in what manner they differ. So this has been the purpose of the present section. So we want to look into how supersonic flow over wedges and cones, right? So let us look into example 3.6. This is a continuation from last week. So now we are going into example 3.6. You want to consider a wedge with a 15 degree half angle, right? We have the theta is 15 degree, right? Half angle in a Mach 5 flow, right? The Mach number is 5 as sketched in this particular figure. So what you need to do is basically to calculate the drag coefficient, CD, for this wedge. Assume that the pressure over the base is equal to the free stream static pressure as shown over here. All right, so let us go through. We have the pressure over the base. So we have pressure denoted as P1, okay, is equal to the free stream static pressure as shown in this particular figure. So consider the drag on a unit span of the wedge as d prime. This is the drag. You want to find the CD, okay, coefficient of drag. So using, we know already d prime of the coefficient of drag is equal to the drag, okay, over Q1S, okay, which is equal to Q1C1, and which is equal to d prime, the drag, over Q1C. From the figure itself, so you want to resolve it accordingly, where we know that the length L, okay, let me just go back, the length L over there, which is the length of the wedge itself, okay, which is equal to the C over cos theta, right? So the C, the cot, right, over cos theta, you get the length, the trigonometry rules, right? So thus you can have this expression and the CD expression in terms of the theta value, right? So we note that from the earlier expression, Q1 equal to 1 over 2 the density times the velocity 1 squared, and you rearrange everything, you put up till the Mach number, and you can then get the value of the CD in terms of the coefficient of drag in terms of the theta value, theta value, as well as the Mach number, which is now, we know it is Mach number equal to 5, right? So from the figure of the graph theta beta Mach number, right? So at Mach number 5, so you trace the Mach number 5, which is here, all right? And you then use the value of theta of 15 degrees, okay? And eventually you will get beta value of 24.2, right? That's how it is being worked out, right? I understand that it's quite difficult to get it as accurate as this value. So if you put it as a 24.0 or 23.8 or very close to it, you should be able to get the same round of errors, so, which is very small. So then you put inside the equation, mn1 equal to m1 sine beta, right? You put the value of beta inside the equation, and you get the corresponding value of mn1, which is 2.05. And then you look into appendix B, for mn1 equal to 2.05, right? We are not going to switch over to the appendix B. You may want to do it on yourself to see what is the corresponding value of the pressure ratio, all right? So from there, you insert the pressure ratio value 4.736 into the expression, earlier expression that we already obtained, and you will then get the value of the coefficient of drag to become 0.114, okay? Note that the drag is finite for this case. In a supersonic or supersonic, hypersonic inviscid flow, over a two-dimensional body, the drag is always finite. Okay, D'Alembert's paradox does not hold for stream Mach numbers, such as that shock waves appear in the flow. The fundamental reason for the generation of drag here is the presence of shock waves. Shocks are always a dissipative, drag producing mechanism, right? And for this reason, the drag is, in this case, is called wave drag, because the drag associated by the oblique shock wave that being generated. And the CD basically is the wave drag coefficient, right? And more properly denoted as CDW. All right. So at the subsonic flight, you are going to experience only CD, because there's no shock wave, right? But for higher speed, especially at this Mach number 5, you will then have to consider the wave drag coefficient, which is denoted as CdW. Right. So that's basically we already cover the subtopic of 3.3, supersonic flow over wedges and cones. And later on in your tutorial, you may experience other examples on the question related to wedges and cones. Right. For the next subtopic, which is shock interactions and reflections. Okay, so this is a 3.4. So we have this figure where we have the we can imagine the shock wave extending unchanged above the corner to infinity. So you have a flow which experience like a wedge-like surface with an angle theta, right? Basically, from there, the shock being deflected and an oblique shock form in this particular manner, right? So you can see here, this is at Mach number more than 1. We have the pressure, the density, and the temperature. And then we have the oblique shock being developed. And we have at region 2, where M2 is normally less than M1, right? Because M1 is it is before the oblique shock. When the flow go through the oblique shock, it is being reduced, right? Similarly with the changes of pressure, the pressure increases, the density increases, and the temperature also increases, right? So, however, in real life, this does not happen. In reality, so the oblique shock in the figure will impinge somewhere on another solid surface. Basically, when it is being deflected, it will then impinges, or it is being reflected onto another solid surface, and or will intersect other waves. So it's not really single line. It is also intersecting with other waves that are already developing elsewhere. So either shock or expansion wave. So this is just ideal case. What happened actually? Because we are looking at the shock interactions and reflection. So in such intersections and interactions, we know it is important in the practical design and analysis when you want to design, for example, for supersonic airplanes, we have missiles, we have wind tunnels, we have rocket engine. We have to consider the interactions and reflections that are happening. Therefore, the purpose of this particular section is to present a mainly qualitative discussion of shock wave interactions. And let us consider an oblique shock wave generated by a concave corner as shown in this figure. So just now in earlier picture, we have only one deflection over there, but actually in real case, right, the flow from region 1, when it is being deflected by an angle theta over there, so you have incident shock. It is going into region number 2 before it is being impinges on another set of wall. All right, this is what we call it as the reflected shock. This is the incident shock. This is the reflected shock. So we have another region to consider over here, which is region number 3. So we have region 1, region 2, and then region 3. All right. So examining the figure, so we have this particular figure again. We see that the flow in region 2 behind the incident. So this is region 2 behind the incident shock is inclined upward at the deflection angle theta. Right? However, the flow must be tangent everywhere along the upper wall. So this is lower wall, this is upper wall. Okay. If the flow in region 2 were to continue unchanged, it would run into the wall and have no place to go. Hence, the flow in region 2 must eventually be bent downward, because when it goes here, it eventually reach a point B over there, then it will be reflected, okay? Reflected and bent downward through the angle theta, right? In order to maintain a flow tangent to the upper wall. Okay, the strength of the reflected shock wave is weaker. Of course, if you imagine a ball being traveled, the kinetic energy of the ball will then, when it hits the other wall, will be lesser, right? Similarly with the flow, right? So the reflected shock wave is weaker than the incident shock. Right? So this reflected shock wave is weaker than the incident shock. And this is because M2 is less than M1, obviously, and M2 represent the upstream Mach number for the reflected shock. So basically, if you have M3 over there, M3 is less than M2, right? So since the deflection angles are the same, whereas the reflected shock sees a lower upstream Mach number, which we know that the reflected wave must be weaker. And for this reason, the angle of the reflected shock wave with the upper wall, we call this as pi, is not equal to B1, right? So this reflected shock angle pi is not equal to B1. So the properties of the reflected shock are uniquely defined by M2, right? Region 2 Mach number, and as well as the theta. Since Mach number at region 2 is in turn uniquely defined by Mach number in region 1 and the theta, then the properties in region 3, the reflected shock region behind the reflected shock, as well as the angle pi, are easily determined from the given conditions of Mach number at region 1 and theta. By using the following procedure, basically number 1, you have to calculate the properties in region 2 from the given Mach number at region 1 and theta, in particular, which gives us value of the Mach number at region 2. And then you proceed to calculate the properties in region 3, which is behind the reflected shock, from the value of M2 that you obtain here, and the known deflection angle theta. Okay, now assume a case that Mach number in region 1 is only slightly above the minimum Mach number necessary for a straight attached shock wave at the given deflection angle theta, right? So for this case, if it is slightly above, the oblique shock theory allows a solution for a straight attached incident shock. However, we know that the Mach number decreases across a shock, right? Because we know when a flow crosses the shock wave, the Mach number will be decreases. And this decrease may enough such that the Mach number in region 2 is not above minimum Mach number for the required deflection theta through the reflected shock, right? So we can see here Mach number, if in this case, in this case Mach number in region 1 is more than 1, Mach number 2 is still greater than 1, you can see a straight shock. But in a particular case where the Mach number in region 1 is just slightly above 1 or equal to 1, you will get Mach number in region 2 which is less than 1. And you will get this, what we call it as the curve shock instead of a straight shock, because they do not, it does not have enough energy. Another type of shock interaction is shown in this particular figure. right? This is another type of shock where shock A, we have a shock A over here is left running wave and shock B is the right running wave. Imagine it is like a inlet of a hypersonic engine, right? So you have a shock being developed above from left to right, and the other one is from right to left. Okay, so where the two shock intersect, there's an intersection point, right? Because this is going to be more complicated, right? We call it the shock A is left running wave and shock B is the right running wave. So called because if you stand on top of the wave and look downstream, you see the shock running in front of you towards the right, right? So this is much more complicated. Across the steep line, the pressure are constant. P4 equals to P4 prime, and the direction but not necessarily the magnitude, the velocity is the same, namely and parallel to the steep line. All other properties in region 4 and 4 prime are different, most notably the entropy. And the entropy S4 is not equal to S4 prime, right? So another type of shock that can also happen depending on the different angles over there, where the intersection of two left running shock generated at corner A and B. So we have the normal first situation A and B with angle theta 1, and then the intersection occurs at point C where we have another shock being produced at theta 2, where this shock, the first one from A to B, this is the shock wave, and then from B to another point we have another shock that being produced, right? So and it intersect at point C where it is then we have the reflected wave, and we have generated another shock over there which is CD, right? So where the two shock merge and propagate as the stronger shock CD, usually along with a weak reflective wave CE. Yes, CE is over here, reflected wave, right? So this reflected wave is necessary to adjust the flow so that velocity in region 4 and 5 are in the same direction. Again, the slip line in CF, right? This is the slip line, trails downstream of the intersection point. So you can see that it's not just only one type of oblique shock. There are reflected shock, and then we have shock being intersect from top and bottom. Okay, and it is also can be considered if we have a complex geometry, right? Okay, now let us look into another example, example 3.7, where we have the case of incident shock wave with reflected shock wave. Remember, this is the case where M1 is greater than 1 and M2 is also greater than 1, where you have a straight reflected shock. Okay, so if you still remember this condition, not this particular one. So consider an oblique shock wave generated by a compression corner with a deflection angle of 10 degree. Theta is 10 degree. And the Mach number of the flow ahead of the corner is 3.6. Okay, so the Mach number at region 1 is given as 3.6. The flow pressure and temperature are standard sea level conditions. Right, so we have to refer to the appendix B later on. The oblique shock wave subsequently impinges on a straight wall. So this incident shock eventually impinges to a straight wall opposite the compression corner. Okay, the geometry for this flow is given here. Calculate the angle of the reflected shock wave. So they want us to find the pi over there, right? What is the value of the pi? Okay, which is relative to the straight wall. And you also need to obtain the pressure, the temperature, and Mach number behind the reflected shock wave. What are the corresponding values of Mach number, pressure, and temperature in this particular region? So we have to start from 1, we find the properties for 2, and then we continue to get the corresponding value at 3. Right? So you have to have a clear mind, clear direction where you want to go to find the values. Let us see the solution. So we start with the diagram of theta beta and Mach number. So you being given a value of 3.6. So there is a trace of line of Mach number 3.6. So you trace it down here and you stop at the point that intersect at theta equal to 10 degree. Okay? You draw a line there. We have a value of 8, 12, 16, 20, 24. So you have to get a ruler and draw a line of theta equal to 10 degree. And the point it intersect with the line of Mach number 3.6, you will then read the value of beta. All right, beta is found here as 24 degree. Using the equation, mn1 equal to m1 sine beta 1. So you put the number there, you will then get 1.464. Right? I hope we are going very slow so that you can follow through the steps. Then, step number 2, you look at Appendix B. Right? So from Appendix B, then you read the corresponding value for mn1 1.464. You will get mn2 to become 0.7157. The pressure ratio 2.32. The temperature ratio is 1.294. Okay, using the expression for m2, okay, you put the numbers in, right? So you know the beta, we know the theta already. You get m2 to become 2.96. So now you have already obtained the values at region 2. So these are the conditions behind the incident shock wave, right? So the incident shock wave, so we have already calculated from 1 to 2, we already obtained m2, and now we want to proceed to obtain the value at region 3. Okay, so they constitute the upstream flow properties for the reflected shock wave. So now you use the Mach number 2, Mach number at region 2, 2.96 as the upstream flow properties for the reflected shock wave. So we know that the flow must be deflected again by 10 degree in passing through the reflected shock, and thus from theta beta m diagram, for now in the case of Mach number in region 2, 2.96, as well as theta equal to 10, we will then get using this chart again. So this particular chart, so you use the different Mach number. Now the Mach number is 2.96. So you have to find 2.96, trace the line, go to 10 degree, you will get 27.3 degrees for beta 2. Okay, note that beta 2 is not the angle of the reflected shock mixed with respect to the upper wall. Rather, of the wave angle beta 2 is the angle between the reflected shock and the direction of the flow in region 2. So basically beta 2 is not pi. Okay, so let us continue. So the shock angle relative to the wall is from the geometry shown in this figure. So basically, you know that pi, the value pi equal to beta 2 minus theta. All right. So beta 2 minus theta, which is 27.3 degrees minus 10 degree, you can then obtain the value of pi, okay, which is 17.3 degrees. Also, the normal component of the upstream Mach number relative to this reflected shock. So use the same approach, okay, put down the numbers, you will then get M2 sine beta to become 1.358. Now it is M3, which is 1.358, which is still more than Mach number 1. That's why it is have a straight shock, right? So you get the M3 from Appendix B to become 2.55 because you have MN3 just now from this equation, okay? So sorry, MN3 is from the table from Appendix B, okay? And you put beta 2 as well as theta, you will get 2.55. For standard sea level condition, we know that the pressure is 2,116 pounds per square feet, okay? And T1 equal to 519 degrees Rankine. So thus, you can then get the corresponding pressure as well as the temperature at the region 3 and the reflected shock region. So note that the reflected shock is weaker than the incident shock as indicated by the smaller pressure ratio. So you have a smaller pressure ratio as indicated. And we know that P3 over P2, which is 1.991 as compared to P2 over P1 is 2.32 for the incident shock. So if you imagine the shock being reflected again and again and again, it will then eventually reduces the pressure ratio and the Mach number. Okay.